I'll get tests. I should be able to get those test scores tonight. So test scores, I don't know, there's quite a few more people got 100. It's all right, but I'll get those in tonight. Reminder, we kind of got booted Friday. I kind of got, if you read the email that I sent you, I kind of got asked to give up the room, but kind of told to give up the room, because the chancellor is talking to these people and flying in, and if you don't give up the room, you got to cancel all the tickets that are already booked. It's kind of a weird email. We looked at it, but it was kind of a weird email. So it's like, we're not really asking you to give up the room, we're telling you to give up the room, even though they kind of asked us to give up the room. That's how I feel about it. So I'm like, I'm not gonna. So Friday reminder, I'll pick out a good recording again. So I guess it is what it is. Okay, let's see. So in the recording I sent you, we got through page 1 and then 1 through 3 on this quiz. And page 1, we went through and calculated the wavelength of AM versus FM on a couple stations. And we talked about the difference in energy based upon the frequency. And we said that, and I did this page a little bit, but I did this page. Frequency goes with energy. The higher the frequency, the higher the energy. It's directly proportional. But frequency and wavelength are inverse of each other. If you have a high wavelength, you're going to have a low frequency, and vice versa. So we're going to go right into a calculation here at the bottom of this page, and it should be this one. The frequency of the radiation used in cell phones cover a range of about 800 to 2 gigahertz, 800 megahertz to 2 gigahertz. What is the wavelength in meters of a cell phone signal operating at 1.12 gigahertz? Now, giga is 10 to the 9. So here's my units. And gigahertz, now this is a frequency. So my frequency is 1.12 times 10 to the 9th hertz. Now, you're not familiar with the unit of hertz, and hertz is waves per second, and this hertz is the same as 1/seconds, and you might see that as s to the -1 for frequency, but that's the unit of hertz. Well, what speed is this going to travel? Well, of course, these waves are traveling the speed of light, 3 times 10 to the 8th meters per second. And our equation is, we know the speed of light is equal to wavelength times frequency. And wavelength upside down backwards, y. So we want to solve this. What is our wavelength in meters? So we'll solve this for our meters. So our wavelength, I'll put it over here. Our speed of light divided by frequency should be our wavelength, right? And if we plug this in, we are going to have 3 times 10 to the 8th meters per second divided by 1.12 times 10
to the 9th, I'm going to put this as 1/seconds for the unit of hertz. So you see that it cancels out. Because if I get a wavelength, the wavelength has to be in meters. I mean, it's going to come out to be meters here. So my seconds are in my denominator here, and my seconds are in the denominator here. They're going to cancel out. Another way to look at this is you could take this fraction down here, flip it, and multiply for the unit. Then you'd have, if you flip this, you're going to have seconds on top. They're going to cancel out with seconds on the bottom. It's another way to look at that. And if we divide that out, we get a wavelength of 0.268 meters. Okay, there's a video here I might bring up, but I have it available. Okay, let's go to the next page. I think we talked about this last time and what a wave actually is. We think of it as two parts. And I believe we added here on this one, we have AM and then we have FM or radio, right? AM has longer wavelengths than FM. Okay. Reminder, visible light is just this small region of what we call this electromagnetic spectrum. Just this small region right here. Again, you don't see the ultraviolet radiation, you don't see the rays hitting your arm like it was 93 degrees last week and say, oh, look at those rays, they're burning my skin. I could see them going right into my skin, right? You don't see in the ultraviolet. You don't see an infrared remote when you hit the button. You don't see, oh, look at the beam go to the computer or whatever you're trying to do, right? I was going to say VCR, but that's really bad, right? VCR or CD player, whatever, but you have a remote control. It's infrared. You don't see that beam going through space. Okay, so when you do the first part of OWL, it just does a lot of which one has a higher energy and stuff like that. Okay, remember our energy goes the same way as this diagram goes. Energy increases because frequency increases this way. They go together. And obviously then wavelength is going to decrease. So the higher the frequency, lower the wavelength, the higher the energy. Again, frequency, energy go together. Higher the frequency, higher the energy. Think of visible light, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Except for now, indigo is kind of like the planet Pluto. They decided it somewhat doesn't exist. So now you don't see indigo. Okay. Red light will have a wavelength of 700 times 10 to the minus 9 meters. So let's actually see where I'm getting that from. Right here. (700 nanometers, 10 to the minus 9. And a frequency of 4.28 times 10 to the 14th hertz, 428 terahertz. Violet light will have a wavelength of 400 times 10 to the minus 9. So I'm going to draw an arrow up to that so you see what I'm talking about here. Frequency, 7.5 times 10 to the 14th hertz. Therefore, the higher energy light is violet, right? You're just comparing, all you have to do is compare the two frequencies. Violet light is higher. Okay. All right, another quick example. The wavelength of orange light is about 600 nanometers. So this is a wavelength. So this would be 600 times 10 to the minus 9 meters. Look for frequency. And we know that the speed is 3 times 10 to the 8th meters per second. What's our equation we've been using? Speed, wavelength times frequency, right? And we're looking for our frequency. Now, this is why you always want to put your units in here, correct? Make sure you're putting your units in. I'm still looking at some tests. I look at the tests and I think, well, how are they getting this wrong? And they're not putting their units in. So we got 3 times 10 to the 8 meters per second divided by 600 times 10 to the minus 9 meters. Now, let me show you the units real quick, because I think you always want to keep track of units. Now, check this out. This is meters per second, right? And now, can I just put meters over 1? Doesn't change anything, does it? Put anything over 1 doesn't change it. And now, if you have a fraction over a fraction, you flip and multiply, correct? So if I just do that to my units up here, I would have meters per second times this flipped 1 over meters, correct? And my meters and meters cancel out. What are my units for this? 1 over seconds. What is 1 over seconds? Hertz or frequency, correct? So you always want to make sure your units. Remember, you don't have to memorize an equation. I probably shouldn't even wrote that down. You just got to make sure you get the right units. We're looking for frequency. We have to end up with 1 over seconds for units, right? We have to end up with units of 1 over seconds. You know, final answer we get out of this is my frequency is really kind of only have one sig fig here. 5 times 10 to the 14th hertz. Okay. Let's go to next page. I probably got too much of this stuff, but again, I've got energy increases this way, frequency increases. This one actually has AM and FM. So depending upon what source you're looking at, I mean, they have things going vertically and horizontally and some with frequency, some the opposite, so. All right, a little bit more of the color spectrum. Here's actual wavelengths and frequencies and photon energies of different colors of light. And notice as we go up this way, energy gets larger. Energy increases along with frequency, correct? Energy and frequency go up, wavelength goes down, right? My wavelength is getting less and less and less. Always, always, always the pattern. Okay. Let's look at this. We can look at the color of something, and the color relates to its temperature or heat intensity. Now, I'm gonna play this video real quick. So I'm gonna stop the share. Hopefully this shows up on the recording. It may not. See if I can get this right. And then I don't know if the video, if the audio is going to come through for this, but
familiar with an electric burner or like on a stove. What's happening here is simply that electricity is being passed through a filament. The filament becomes resistive, heats up, and it reaches sufficient temperature that it starts to glow, starts to give off an least visible light. Now, we also know that we increase the temperature by running more electricity. Not only does it seem brighter to us, but it actually seems to change. And it's this reddish color to a more orange color, to a little higher temperature. This is a phenomenon referred to as incandescence, giving off of visible radiation. This is called a black body radiation. No matter what the material is, it's not sufficient temperature to get this emission of different frequencies of light. Another place that we will see this that we're very familiar with is the incandescent light bulb. And the idea here is exactly the same as it has electricity through a filament. This is resistive. Again, it's resistive, so it heats up the temperature that we get visible radiation. That's simply because the temperature is different. It's the higher temperature, so we see different, as we see a different color than the lower temperature. Now, remember that we know that the light is actually a mixture of many different frequencies. So we can imagine taking that light, passing it through, let's say, a prism, which allows us to separate out all the different frequencies of light. And we can analyze frequencies that are different. How much of those different frequencies we get? So if we do that, we get a code, total black body radiation. Now, what happens here on the blue curve? Let's take a look at this. So I'll just stare here. This is wavelength of the light. And the wavelength is inversely proportional to frequencies. We have a long wavelength and a short wavelength. Low frequency, high frequency. And you'll notice that as we go to higher and higher frequencies, that the amount of light that we get increases. Higher intensity is the more this curve. Now, notice what else happens. You reach a P. This P will correspond to C that is the greatest intensity at a particular temperature. Now, this curve, just to clarify here, this curve is only for one temperature. And then the intensity of the signal. Slides. See the data. Remember we said that will change as a function of temperature. So if I look at another, but at a different temperature, this says higher temperature. And what will happen is we will now, and it must have been so that the light is above here and cools. So again, we see the so the area because why does this happen? Why do we get frequencies of different intensities of the something that helps us understand what that.
Okay, you get an idea. You can watch this. It's a good video. In Canvas, there is a link to these. And some of these are pretty good. I've got to be cognizant of time. So that gives you an idea of what we are talking about when we get intensities, and the intensity or energy is associated with temperature. So if you have something on the stove, you saw the first coil that was, orangish hot. If it turns green, it's going to be higher intensity, higher heat. It relates, color relates. Where that came from was the firing of clay way back. You looked at the firing of clay, and the bottom of the clay pot, was a certain color. And that was kind of the beginning of the science of that. Okay. So 1900, German physicist Max Planck proposed that light, heat, and other forms of radiation come in tiny bundles, which he called quanta. Planck assumed that the electromagnetic radiation emitted was caused by vibrating atoms called oscillators in the heated object. Okay. He proposed that each oscillator had a fundamental frequency, and we want to change this to F for our frequency. We've been using F of oscillation, and that the emitted radiation could have only certain energies given by this equation. Okay. And I am going to change this. Your textbook, I believe, uses the V. I'm going to use HF. So I'm going to rewrite this, right? This is going to be F here. Now check this out. This is Planck's equation. The energy is given by change in N. What is change in N? Is the change in energy level. Change in energy level. Well, you probably at one time have seen some kind of diagram where we have electrons at energy level 1. If I go on to page 9, somewhere in your science classes, you have some diagram that looked like this and said, oh, we have 2 electrons here, we have electrons here, and the next level it was referred to, we have more electrons, right? Somewhere along the line, you've seen a diagram that looks like this. I can almost guarantee it. Okay. Now, these electrons are at certain levels, kind of like if you have a ladder, you can't step between the rungs of the ladder. So you can think of this, if I put a ladder right here and spin it into a complete circle, I would create something like this at certain levels, correct? For sure, I'd have certain levels, and those electrons can only be in certain levels. But we know if we put energy into an atom in the form of electricity, heat, or light, we can kick these electrons farther out away from the nucleus, and they come back down and they give us energy back. So we know these electrons don't necessarily stay stationary. But again, if we kick them out farther, they come back down. So we know electrons can change levels. All right, so we have Planck's equation actually gives us the fact of our energy, and it would make sense if you have a higher waterfall, you have more energy at a higher waterfall. If we have an electron farther out, it attains more energy. Okay, so this is our equation. This is Planck's equation, change in energy level. H is Planck's constant, and F is our frequency. If change in energy level is just one, there is a change from one energy level to the next lower one. F is frequency. And H is a constant that came to be called Planck's constant. And notice the units are in joules times seconds. Planck proposed that energy is quantized. Quantization means only certain energies are allowed. Again, if we spin that ladder in a circle, you're only at certain levels you could go to. Okay, Einstein expanded on Planck's work to explain the photoelectric effect. Einstein proposed light can be massless but particle-like, and he referred to them as photons. A photon is a packet of light of discrete energy. Photons strike atoms on the metal surface, causing electrons to be ejected only if the photons have high enough energy. So I pulled an illustration from your textbook. Here's the photoelectric effect. What is this? This is a photocell. So if this light of certain photons hits this metal surface, nothing happens until you get high enough frequency, and then electrons are ejected. And obviously, if you have higher intensity light, you're going to get more electrons ejected. But again, for this to happen, there has to be a high enough frequency of light. It's that simple. For the photoelectric effect to take place, it has to have a high enough frequency, which is high enough energy. Okay, so Einstein proposed the photoelectric effect, and the relationship of energy, wavelength, and frequency now goes into one equation. Let's fix this thing up. I'm going to put an F here for frequency. Now, so here's what we've got. So our energy is equal to Planck's constant times the frequency. But if we solve the equation, C is equal to lambda F for frequency. If I just solve this for frequency, I would have C over lambda, right? So that's what happens then, is we could substitute this in for frequency. If we wanted to, if we didn't have the frequency, we just substitute that in. So here's what we have. We now have an equation. Our energy is equal to Planck's constant times the speed of light divided by the wavelength. Here is all of my units. We know C is in meters per second. Planck's constant is in joules times seconds, and our wavelength is meters. Our energy comes out to be joules per photon. Joules per photon. Now, this also verifies what we have been saying. Looking at the first part of the equation, as frequency increase, energy increases, right? If frequency goes up, energy has to go up, right? And vice versa. Looking at the second part of the equation right here, as the wavelength decreases, energy goes up. As this denominator here, as the wavelength gets smaller and smaller and smaller in the denominator, doesn't the result get bigger and bigger and bigger? Right? Mathematically, wavelength gets smaller and smaller and smaller. This energy then would get bigger and bigger and bigger. Again, all starts out, and I don't know how many questions are basically just this. Okay, so here's an example problem, and then I have a not so ugly owl, so you know exactly what you're going to see in the owl homework. All right, compact disc players, now obsolete. I'm sure all of you in here have seen a compact disc before, hopefully. Probably even a VHS tape if you're really ancient. All right. All right, that compact disc player uses lasers that emit red light with a wavelength of 685 nanometers. So nano would be to the -9 again. What is the energy of one photon of this light? Okay, and the problem is we're going to get this into kilojoules per photon is what we want for units. Now, let's write down our equation in the green sheet that we had way early on. I believe I put these equations up there. Once I copied the wrong green sheet. Yes. So on the green sheet down here is kind of the spot that I did a summary of what we're talking about here. So here's our equation. So this green sheet might be handy. Okay. Let's see what we got here. We know that our energy is equal to Planck's constant times the frequency. I have a wavelength. So I'm going to make the substitution that this is equal to our speed of light divided by our wavelength. That's what our frequency is. Okay. I am going to plug this in right here. Planck's constant, H, is 6.626 times 10 to the minus 34 joules times seconds. My speed of light, 3 times 10 to the 8 meters per second, divided by my wavelength of 685 times 10 to the minus 9 meters. And it wants it in kilojoules. So I'm going to change this to kilojoules here. And that's simply going to be 1,000 joules into 1 kilojoule. And this is going to come out to be in kilojoules per photon, 2.9 times 10 to the minus 22 kilojoules per photon. Okay. So we're just plugging in equations. All we're doing is plugging in the equation. Not so ugly owl, I've titled this. So this is a direct owl question. Doesn't seem too bad, but let's see if we can figure it out. A local AM radio station broadcasts an energy of 4.96 times 10 to the minus 31 kilojoules per photon. Calculate the frequency at which it is broadcasting. And notice my units need to be in kilohertz. All right. So let's see here. We've got our energy of 4.96 times 10 to the minus 31 kilojoules per photon. We're looking for our frequency. So let's write down our equation first. All right, so we know energy is equal to Planck's constant times our frequency. We want frequency, so I'm not going to do my substitution I did for the last problem. I'm just going to leave this as the frequency. So then I know my energy divided by Planck's constant should be my frequency. And my energy is 4.96 times 10 to the minus 31 kilojoules per photon. Now, I know Planck's constant is in joules. I know Planck's constant is in joules, so let's change this to joules. 1 kilojoule, 1,000 joules. And now I'm going to divide this by Planck's constant, which is 6.626 times 10 to the minus 34 joules times seconds. So joules will cancel out, kilojoules will cancel out. Seconds is in my denominator. So I have a frequency. So this comes out to be, I'm going to write down all the numbers. What my calculator would give me, 748,566 hertz. But I want this in kilohertz. So 1,000 hertz in a kilohertz. So 749 kilohertz. Okay. So 749 kilohertz, that's an owl question. All right, the next is the photoelectric effect. We're going to talk about atomic line spectra in Niels Bohr. Okay. Again, we know that the electrons are at certain energy levels. We know if we put electricity into the atom in the form of electricity, heat, or light, these electrons are kicked farther away from the nucleus. It's going to absorb that energy, and then eventually they're going to drop back down because they're still attracted to the positive nucleus, and they're going to give us energy back. It's no different than throwing a water balloon up in the air. The higher we throw it, the more energy it has, correct? But it's going to drop back down. And we could get that energy back if you wanted to bop your friend on the head, correct? I mean, your friend would get hit with some energy. So again, we know the electrons can go farther out and they come back down. Well, when they come back down is where we see visible light. When we come back down is where we see visible light. And I want to show it right here on page 11. So on page 11, shows us that this is called the Balmer series. This is visible light. Notice that we only see visible light when the electron drops back down to energy level 2. Energy level 2, we see visible light. This drops back down to energy level 2. This rich passion series drops back down to energy level 3. This is infrared. And if it drops back down to level 1, this is UV radiation. Again, we see visible light when the electron drops back down to energy level 2. That's when we see visible light. Not only that, we can run that through a prism or something, and if we have a certain gas we are talking about, we're going to talk about hydrogen a lot, we actually can figure out the exact energy, frequency, and wavelength for the colors that we see. Okay, so notice that, and this is what Al does a lot coming up, and we'll talk about on Wednesday. If the electron drops back down from energy level 3 to energy level 2, that's red light. How does that compare if the electron drops back down from energy level 6 to energy level 2? That's violet light. That's a lot more energy, correct? It's a bigger drop. It's more energy. And from these drops, we can calculate it all. Okay. So let's go back. And now you're going to understand that we can actually calculate these energy drops. So now I have to go back to page 8. So on page 8, this is what happened. We know that if we have hydrogen gas and separate the light out, light is separated into component wavelengths by a prism or a diffraction grating, we actually can separate these colors out. So these are the colors. And this is what happened. Trying to interpret the 4 colors found in the emission spectrum of hydrogen, Johann Balmer in 1885 derived an equation relating to 4 other wavelengths. Rydberg went further by developing an equation for wavelength in the visible and not visible region. And notice that this is our wavelength. This is the energy levels. Notice this drops back down to energy level 2. This is our energy level higher. Okay, so now we have an equation that we could solve this for our wavelength, right? And you may know if 1 over the wavelength is equal to 2, we flip both sides, the wavelength would be a half. Okay, so now we have this Rydberg constant in meters to the -1. And I've calculated this out. If you put 3 into this equation, you calculate red at 656 nanometers. If you put 4 into the equation, you calculate green at 486 nanometers. Okay, we will calculate some of those out. Let's get there because we're going to use this equation next time, but let's finish this up right here. So in 1913, Niels Bohr proposed a planetary structure of the atom in which the electron orbiting the nucleus would emit or absorb a photon if it moved to a different orbit, higher energy level, right? We're spinning a ladder. Or this looks like a planetary model, correct? Where the sun is at the center. When an electron is in the lowest energy orbit, the atom is said to be in the ground state. If the atom receives energy from an outside source in the form of electricity, heat, or light, it is possible for the electron to move to a higher energy orbit, and the atom is now an excited state. Added energy is absorbed. It's going to move to a higher energy orbit. When the electron returns to a lower energy state, energy is released in the form of electromagnetic radiation. The diagram shows the energy states of the hydrogen atom. Only the Balmer series is visible. The energies of electrons, energy levels in an atom are quantized, described by quantum numbers, integer numbers having only specific allowed value and used to characterize the arrangement of electrons in an atom. The electron's energy increases with increasing distance from the nucleus. And that's what we looked at earlier. Okay, we can probably can we do another quiz question? Try number 4. So try number 4. You should be able to calculate that in the number 4. So on this quiz, do 1 through 4. Next time we meet, we're going to end up doing a lot of these calculations so you can get through out.